Thank you, Jaykumar. Thanks to the organizers for organizing a splendid workshop and inviting me here. And thanks to all of you who are sticking around until the finishing line. So this is joint work with my student Shagnik Mukhopadhyay at TIFR. Okay. So let's get started. So I'm going to talk about the message passing model, which was talked about in the morning earlier by David Woodruff. So here we have multiple parties, and they are connected by an underlying graph. And the inputs are in the hand. So it's a number in the hand model as opposed to a number on the forehead model. So the communication, as David was alluding to, is point-to-point through private channels. So messages are sent from one node to the other node through a dedicated channel which others cannot access. Okay, and you are charged for each message sent across all the edges. Typically, there would be k nodes in the network which will have inputs, and there might be other nodes in the network which do not have inputs, but they may facilitate in the computation somehow. And there's an underlying graph G, as I said, and these nodes want to compute a function f, which depends on those k inputs x1 to xk, and the players or the nodes have private randomness. Okay, so this is the model that I'm generally interested in. And what we want to understand is the total communication. So the total communication is the, as I said, the total number of bits that flow out on all the edges of the network. Okay, and it should depend, as you might very well expect, the total communication should depend not only on the function f, but also on the underlying graph G, the topology of the graph, right? This area is very little explored, so there are lots of open problems here. But I will, henceforth from now, actually focus on a very specific topology. And at the very end, I will tell you how results obtained on that topology could be lifted to arbitrary topology. Okay? So the topology that I would be interested, as David was, is the star topology. It's also called the coordinator model. So here, there are k nodes which are connected by a star, so that the central guy here is the coordinator who doesn't get any input. These are the nodes, the leaves, that get input, and they want to compute some function. And as you can see from the topology, they basically cannot communicate directly to each other. They have to always send their messages to the coordinator, who then directs it to some other node. Okay, so as I said, this is called the coordinator model, and it turns out convenient to analyze this model. It has been quite extensively looked at in the literature. And one thing to notice, as he also said, David, that if you have an arbitrary graph, these two models are about 2 log k apart in terms of total cost, right? Because, for example, if this is the complete graph, which is very well connected, any message that player 2 sends to player 3, or between any two players, can be sent correspondingly via this path, right? And so this player has to tell the coordinator who this message is meant for. That takes log k bits. And instead of one hop, there are 2 hops. Okay, so it's 2 log k. So if I prove sufficiently strong lower bounds in this model, it will give me corresponding lower bounds in the other model as well, except with this factor log k loss. Okay? And as I said, at the end, we will see another benefit of the star with respect to proving lower bounds for general topology. Okay? I'll just mention that. Okay, so as a warm-up example, let's look at this equality function. Very simple function, where the k nodes get n-bit strings. So each xi is an n-bit string, and all they want to verify is if all the strings are the same string or not, right? So the naive protocol is an nk-bit protocol, where every player sends its bits to the coordinator, and the coordinator just outputs the answer. Right? And as you might expect, well, for equality in a deterministic protocol, so currently, sorry, I just forgot to mention, I'm looking at the deterministic setting in this warm-up example. I'll come back to the randomized setting later. So in the deterministic two-party model, which is a very special case of this star topology, equality cannot be done any better than the naive protocol, right? So you'd expect that NK is the best that the players can do. Is it true? So here's a tempting way to analyze this. So I'll use this notation pi for the transcript of the protocol, okay? And pi I would refer to the transcript as viewed on this link, okay? So what we might hope is the following. So pi, the length of pi is just the sum of the lengths of each of these pi i's, okay? And let's have a cut which separates the player, let's say player 2, from the rest of the graph, and then you might hope that, well, it now boils down to a two-party equality problem between Alice and Bob, where Alice simulates player 2, Bob simulates the rest of the graph. And don't we know that pi 2, the length of pi 2 is omega n, because it's a two-party equality problem, and therefore aren't we done? Because we just sum up the thing for each of these pi i's and we get omega kn. So do you spot a problem with this argument?
Two-party equality.
Sorry?
It's not a two-party equality. It's a different relation.
Well, if I, for example, assume that, well, that's one problem, surely. But if I assume that all the players are getting the same input.
Well, I guess the question is whether you reach the maximum everywhere at the same time, right?
That's right. So the point is, well, the way I stated it, it is the worst case cost, right? Two-party equality has worst case cost. So it is true that at some point there will be about n bits flowing out here, and n bits flowing out in each of these links, but they may not necessarily happen for the same global consistent input, right? So there's a simple way to get around this problem, okay? And it turns out to analyze the randomized model is much more convenient when you have these graphs, because then these two-party cuts can provide you a very convenient way to analyze things. So what we will say is the following. Let's choose a uniform. Let's choose the following distribution, mu, which is uniform over, all players getting the same n-bit string. Okay. So then if we look at the same cut again, it's not hard to see that this induces a two-party equality problem where the other players here on this side, Bob's side, collapses to one node, and you have a two-party equality problem where the distribution, the underlying distribution across this cut is the uniform distribution over xx, right? And here we know, in fact, that not only is it omega n, the expected communication cost is omega n over this distribution. Okay, and just now by linearity of expectation, we are done. Okay, so it becomes easier somehow in this model to analyze the randomized, in some sense more convenient to analyze the randomized cost of protocols whenever you can. In fact, I wouldn't have the time, but there are many interesting problems for which are randomized easy here, and it's hard to prove deterministic lower bounds. Okay, if you want to hear about this, I can tell you offline after the talk. Okay, so as I said, our focus would be on randomized lower bounds. So basically using that same idea, or the basic idea that I just explained by looking at the expected cost rather than the worst case cost, this Phillips, Verbin, Zhang in 2012, they came up with a very elegant paper and a technique called symmetrization, which they used to prove lower bounds for various functions. The point was these functions were, although not Boolean, okay, they had multiple output, and they could prove various lower bounds for a bunch of functions where you looked at these functions were of the type where you were looking at either bitwise OR, bitwise AND, or bitwise XOR, and so on. Okay, so as I said, these functions were instead of being Boolean, they did output n bits. And for each of these cases, they could show using this symmetrization idea that the lower bound is omega nk. And later, Woodruff and Zhang, in subsequent papers, built upon this idea. And in fact, they proved lower bound, as we saw earlier today as well, for Boolean functions, which still match this omega nk. However, For simple Boolean functions, like let's say set disjointness, so here I'm talking about the k-party generalized set disjointness, or the generalized inner product. Okay, these are set disjointness and inner product happen to be two cardinal functions for two-party complexity, so there is a natural k-party generalization. For these two functions, there were no lower bounds known. In fact, it was not known whether you can sort of reduce these problems to their two-party analogs via this cut technique. Okay, so it is still not known whether you can do that. Sorry? Is there a new paper?
Curious, are you sure for generalized inner product you can't do it with a large enough alphabet? Or?
So I'm looking at the binary alphabet.
Oh, this binary. Okay.
Yeah. So, however, in this paper by Braverman, Ellen, Oshman, Pitasi, and Vaikunthanathan in 2013, they showed a technique to prove omega nk lower bounds for both set disjointness and inner product. The bound is stated in terms of set disjointness, but it obviously gives you lower bounds for inner product as well. And they use information theoretic techniques. And this technique seems to sort of fundamentally differ in the sense that they have to analyze it as a true k-party protocol rather than reducing it to cuts and looking at two-party protocols across cuts. Okay, and we are going to build upon this technique here. So what's set disjointness? I mean, this needs no introduction, but let me still go through quickly. So you have k players, they get each a set from some universe of size n, and what they have to find out is there a common element in all of their sets? Okay, so let's look at the bits of set disjointness. So you have basically you have this k player. So I'll view it as a k by n matrix because the universe is of size n. And what the players are interested in doing is to find out if there is a column out of these n columns where you get all ones. Okay, that's set disjointness. And in terms of a formula for this, it's not hard to see that it's just an OR of ANDs, where the OR has a fan-in n, and each of these ANDs has fan-in k. Okay? So that's the formulas. Now, the function that we will look at is a natural generalization of set disjointness. So this is a depth 2 formula. It just is natural to consider now a depth 3 formula. Okay, so that's a depth 3 formula which is basically trying to compute the AND of m many copies of disjointness. By the way, I should just mention here one thing that I think this was also done by David. Although I'm calling it set disjointness, technically it's non-disjointness. Okay, but I will continue to call it disjointness. Okay, so now I'm looking at this function called tribes, which outputs 1 if and only if m distinct disjointness all output 1. Okay, so it becomes a depth 3 formula instead of a depth 2 formula. And again, naively, it seems that the best thing that one can do is to solve this individual disjointness, m of them, separately. Okay? And this problem has been looked at in the two-party context quite a bit. So the particular setting which makes it interesting is when I have this fan-in m and this L about root n. So remember, m times n is the total number of columns, the length of the input n. And now let's make m equals L equals root n. Now the interesting thing to note is, with this setting, tribes has both non-deterministic and co-non-deterministic root n bit protocol, which means that if you use corruption bounds or discrepancy bounds, you're going to get at best root n. In fact, I think that was historically the first reason to look at tribes in the context of communication complexity. So this paper by Jairam Kumar and Sivakumar in 2003 showed, in fact, for k equals 2, this naive protocol does the best. And they used, again, information theoretic techniques. Okay? And in 2009, Hartmut Klauk's paper implied, which showed a strong direct product theorem for set disjointness, which also implies a lower bound for tribes. Okay? So even in the two-player setting, information theoretic techniques become very important for proving lower bounds for tribes. So we can expect, or it's very natural to try to lift those information theoretic techniques in the context of the number in the hand model, multiparty. So that's what we do. So our main result is to show that tribes remains very hard. It's randomized the knife protocol essentially is the best protocol. The randomized complexity of tribes is m times L is n, so it's nk, okay, in the coordinator model. So the rest of the talk, what I will do is I will first start with the main ideas that went into the proof of set disjointness. So one has to understand set disjointness well enough to talk about tribes, so I'll talk about set disjointness and some of the ideas that come there, some problems that I want to show you, which basically tells us why perhaps the cut technique doesn't quite work, and then how this paper of Braverman et al. Get around it, and then what happens when you try to extend that technique to tribes, the problems and the way around. So I will not go into any proofs, I'll just give you the ideas. Okay? And the problems that I will describe have already been observed. Actually, some of the problems were already very nicely described in this earlier paper of Phillips, Verbin, and Zhang. I will follow the way it has been described in Braverman et al. And then the way around our solution to tribes is basically going to be a combination of the techniques coming from this paper of Braverman et al. And lifting the Jairam et al. Paper to the level of multiple players. Okay, let's get started. So there are going to be two key protocols that one needs to take care of when understanding set disjointness. Okay, they basically outline. I mean, they have two very differing features, and that basically highlights the problems in analyzing set disjointness in this particular model. Okay. So what are these two protocols? One is the very naive protocol, where all players send, each of these k players in one shot simultaneously send their entire input to the coordinator, and the coordinator gives the answer. It's a obviously very dumb naive protocol. I'll call that protocol simultaneous. Since we're going to use information theoretic techniques, it's important to understand from the point of view of information theory what players are learning and who is learning what. Okay? So in this protocol, observe that the players obviously do not learn anything because they've sent it all to the coordinator, but the coordinator might learn a lot if the input has high entropy. Okay? Then the coordinator gets to learn a lot. Okay? And let's now contrast it with the other protocol, which I'll call the polling protocol. So here the coordinator is going to poll individually each player for each column. Does this player have a 0 or not in that column? So he takes turn in polling one player at a time. So he tries to find out from player 1, have you got a 0 in column I? Player 1 perhaps says no, then he goes to player 2, player 2 says no, but then player 3 says yes, I've got a 0. And so for this column, he does not need to poll the others, right? Because in this particular column, he knows this cannot be responsible for intersection. Okay? So, and then he repeats this for each column. So it's a very simple protocol, but it's quite different in some sense from the first protocol, right? Here, the coordinator may not learn a lot for each column. In particular, it may not learn omega k bits for each column, okay? Because the things might end very early, okay? Unless you design your inputs the input distribution very carefully. But on the other hand, again, if you have designed your input distribution carefully, the players who do not get polled may learn from the fact that they did not get polled 1 bit. Each player who doesn't get polled learns on the average. Again, if you design your distribution well, he learns that, well, I didn't get polled, so that means players before me, some player before me got a 0. So if the 0 was uniformly distributed, then players in the middle would learn about a bit. Their uncertainty was half in terms of whether the 0 occurred before me or after me. Okay? And so each of those middle segment players learn a lot. The other thing to observe is, the interesting thing is that, if you look at the communication rather than information, across a cut, since this is sort of varying, across a cut, not necessarily 1 bit is flowing for each column. In other words, there may not be a cut where omega n bits of communication is happening. On the average, somehow, things are happening as expected. Okay? So these are the two opposing, and you will see that in order to design this distribution, the right distribution where you either charge the coordinator or charge the players, you have to design a distribution that balances this both two sort of opposing demands. Okay? And the information measure therefore should look something like this. One part of it should account for the fact of the players learning, and the other part should account for the coordinators learning. Okay? So this part is to take into account the polling protocol, because here you expect, if you design your distribution well, that the players would learn a lot about the other player's input. And for this part, you need to design, as I said, a distribution such that the observer or the coordinator who has no input learns a lot about the inputs. Okay, so how would our distribution go? Well, first of all, from our two-party understanding of set disjointness, if you want to, eventually we want to say that you can't do anything better than basically learning each column, right? So you have to have your distribution supported entirely on the zeros. Each of these ANDs, this is a standard thing that we do also in two-party, so that's a no-brainer. So you have to have supported on zeros of ANDs, okay, so that you get a direct sum. And then, as I said, in order to beat the polling protocol, you need to hide your zeros well, smoothly. Okay? So here's how the polling protocol goes, perhaps. And so you need to hide your zeros well so that it probes deeply. And again, to beat the simultaneous protocol, you want your inputs to have sufficiently large entropy. Omega n, it should have at least nk bits of entropy. Otherwise, you can't hope to prove an nk bit lower bound, right? So for instance, if you were to design a distribution which had exactly in each column 1 0 uniformly hidden, that might be good for the polling protocol, but it's not good for the other protocol because that only has n log k bits of entropy. Okay, so the coordinator wouldn't learn much for the simultaneous protocol. So how do we do that? So we're going to look at the distribution that Braverman et al. Came up. So the input distribution is going to be the following. Now, the coordinator, it's going to be a convex combination of two distributions. One accounting for the polling protocol and the other accounting for the simultaneous protocol. So it will be switched, and this switch will be owned by the coordinator. That it would be convenient to think of it in that way. So there will be two auxiliary random variables. One I'll call Zj and the other Mj, J for the column. So Zj indicates for column J, where do you hide the 0? Okay? And so whatever the value of Zj is in that particular column, at Zj you will always put a 0. Whereas Mj is a Bernoulli random variable. It has two possible outputs, A or B. And corresponding to A, you have the following distribution where you have exactly 1 0. Okay? And the 0 is where Zj indicated it to be. And then B is, well, again you have 0 where Zj indicates it to be, and then the other bits are completely chosen at random between 0 1. So notice that this protocol B has distribution B has high entropy, and distribution A does not have high entropy, but it hides 0. So roughly you would think that with half-half probability, you do that. For technical reasons, it's not exactly half-half, but we'll pretend as if it's half-half, okay, for simplicity. Okay, and the information cost of a protocol, sorry, there should not be a function here, just pi, so we're going to modify it slightly as well, since we can, without loss of generality, assume that these switches are owned by the coordinator. The coordinator does not get any input, but he gets this M and Z. Okay, so this first part basically represents what player xi learns from his local view of the transcript about, and this switch M, and this switch M turns out to represent the knowledge of the inputs of the other players. Okay. So this sums up this is the cost of this is the information that player xi learns. Similarly, this is the information that the coordinator learns about xi's input, and we are going to sum it over all players I equals 1 to k. Okay, and it's quite technical and involved, but Braverman et al. Were able to show that under this distribution and with this notion of information cost, disjointness admits a direct sum, okay, and the cost of computing one and of fan in k is omega k. So if you put these two together, you get your omega n k information complexity cost. Okay, so let me quickly move to tribes. Now what happens with tribes? Well, again, the main point is what distribution should you put? So again, the first part is, well, ideally you would like to get the direct sum for free, but now at the output you have an AND gate. Okay, so if you want your direct sum, it has to be supported on the ones of set disjointness. Okay. Now, let's look at this disjointness. So now this instance, each instances of disjointness have to output a 1, and this is different from what we were doing before, right? Because what we did before, or for normal two-party set disjointness, you look at the distribution entirely supported on the zeros of set disjointness. Okay, so how do we do this? Well, this is an idea that appears in JKS as well. Is we choose a random. This fan-in is L, so we choose a random variable, a random wire here, and then we say that this particular, if Wj points here, we say that this particular instance is going to output 1, and the other instances will continue to output 0. So you're going to hide the 1. Okay, that's a very natural intuition, because you still want the protocol to search for this 1. Okay, and other inputs get assigned as before. So how much time do I have? So I'll have to rush through this. So what's going to be our measure of information cost? Just as before, the information cost measure remains basically unchanged, except now that we condition on this extra variable W, which indicates for a particular disjointness instance where do you hide the 1. Okay. And the first direct sum theorem basically goes through verbatim as in Braverman et al. Okay, believe me, it doesn't take. You essentially follow your nose, and you can prove this, that the first direct sum goes through. Okay, now what we want to do is, we are in this problematic situation, because now we want to prove that the disjointness, the information cost of disjointness, also admits a direct sum. But before we had this zero distribution on the zeros of set disjointness, and now we have the distribution on the ones of disjointness. So what we need to do is to get a direct sum for distribution supported on the ones of set disjointness, right? And this is the crux of the problem. Okay, and then here again, this problem was of course faced in the two-party context by Jairam et al. And we take the cue from there. Okay, so how do you do this? So imagine that you have 1 on this particular wire. Okay, and so of course what you want is to embed a disjointness or AND on a smaller set of inputs somewhere here. So given a protocol for a larger instance of set disjointness, you want to solve set disjointness over smaller instances embedded as many places as you want, and bring down the information cost. Okay, that's the rough idea, right? So as soon as you have a 1 marked on a wire, you see that you have to hide that 1, because if you expose that 1, if you embed your smaller set disjointness instance in a way that exposes this 1, you cannot carry forward the direct sum argument. Okay, so what you do is you hide your 1. You have to embed the place where you have a 1. You have to have it under your control, and you cannot use the other things. So that leaves only L minus 1. If the fan-in was L, it leaves only L minus 1 degrees of freedom. So at best you can hope for L minus 1 times something, right? And that times something, the right, also you have to modify this information cost, because you can't work with your normal information cost measure before, because you have to constantly hide this particular place which was flagged for a 1. So you modify the information cost. This is basically lifting the definition of the partial. This is called the partial information cost. This was introduced in the work of Jairam et al. And we, along with the new distribution here, we modified so that it just looks like that. And what we are able to prove then is that this partial information cost admits a direct sum, but now you get L minus 1 times the partial information cost, not over 1-bit instances of n, but on 2-bit instances of disjointness, which was also similar in the case of JKS. But making this direct sum go through requires some interesting application of the chain rule of information, which doesn't seem to appear in the Jairam et al. Work. I won't be able to get into that. Okay, and then the second thing is to prove that just as before, that now that under this new distribution, the 2-bit disjointness has partial information cost omega k. Okay, so I'm running out of time. Let me just quickly put things together. So what have we done? So we have defined this information cost and shown that information cost of tribes admits a direct sum. This was not hard, given the work of Braverman et al. Then we took ideas from Jairam et al. To show that, to define a new measure called partial information cost, and then information cost, this is not again hard to see, is at least partial information cost. The main new ingredients are these two, where we show that the partial information cost admits a direct sum, and in terms of the 2-bit disjointness, and then you show that the partial information cost is omega k bits cost for 2-bit. Okay. Last thing, I promise that there is something to be had about general topology by analyzing this star graph. So in some recent work with Atri Rudra, what we were able to show is that if you look at a general graph, so completely arbitrary topology where you have k terminals, but the graph might have other non-terminals which have no inputs, the cost for computing disjointness or tribes is what you would expect by the naive protocol to be, which is n times the Steiner tree cost, the minimum Steiner tree cost of connecting these terminals. Okay? So in fact, what we show is something very general, which is basically whenever you can prove a good enough lower bound on the star topology, this lifts up to being the Steiner tree type cost for a general graph. Okay, so it's nothing special about disjointness or tribes. Okay, thanks for your attention.
Can you say a little bit about the reduction to the 2-bit disjointness problem? I don't remember how they did this.
So you would embed this I and j of the 2-bit at random. This is roughly what they do, but what you have to do here in addition is, so the coordinator will sample a few things. So there are the switches M, Z, and W. So the coordinator will also look at a random set of size something. Okay, so it will look at a random subset of 1 through n, and for this random subset of 1 through n of a certain size, okay, I'm not telling you the details, he will sample this M, Z, and W for that random subset, okay, and then transfer it to the players, who will then, using their private randomness, sample their inputs according to this M, Z, W. And for the remaining, he will sample the whole inputs and transfer it to the players. Okay, and if you analyze this protocol and use the chain rule of information, you can show that this, yeah. But we can talk about more details offline.